Hey everyone, welcome back to this channel. In this video, we're just going to go over an example final. This is available on Canvas, and this should be probably the last video that we'll have for this quarter, I'm suspecting. So here is the example final. It is 5 questions. Each question is, broken down into 4 parts, about quarter of a point for each part, so 10 points in total. And all of the circuits are, pretty familiar to what we've done in lab for the most part. I think the only one that might be a little weird is number 4 and number 5. We're looking at kind of like a design type question where I'd hand you a device and we try to figure out what we want to do with that device. And on each page, we'll include these little references, um, for the questions. I think that they should be sufficient for all that we need. Um, But just taking a look at this first question, we've got the DC model of that residential power distribution circuit. And for part A, we're looking at how many unknown node voltages are there. So on this diagram, this figure, we've already labeled ground. So this is 0 volts. And these voltage sources are constant. So we know at this node, we're at a voltage of V2. And at this top left node, we're at a voltage of V2 plus V1. So we've got 3 unknown node voltages on the right here. So here's 1A, node B, and node C. So we've gone ahead and labeled those. And then right here, I'll just write that there are 3 unknown node voltages. And for the second part, we are going to label current directions and determine a system of equations. So I'm going to label a bunch of currents. For R1, I'm going to have I1 flowing through it, and I'm going to draw all of my currents, such that they flow through the system and return back to ground. So R2, or I2 is going to flow through R2. I'm going to label all these respective to their resistor reference designators. And we're returning through R6 here, back to ground. So to find our system of equations, we're going to use a KCL statement at each node, at each of the unknown nodes at least. So KCL at node A, just taking a look at A, we've got I1 going in, I2 and I4 coming out. I1 minus I2 minus I4, and this will all sum to 0. So if you forget Kirchhoff's current law, I've written it down here. And so the current into a node is equal to the current out of a node. Or we could subtract off the currents going out and that will be equal to 0. So then looking back at our diagram, our figure here, so I1 is, we're starting at V2 plus V1, we're going to VA, so we subtract those and then divide by R1. V2 plus V1 is quantity minus VA divided by R1 plus, oh, actually we're subtracting I2, so VA minus VB divided by R2. And we're subtracting off R4, because VA minus VC divided by R4. And this will all equal to 0. So here's one equation. You don't need to simplify it more unless you want to, I guess. So our next step is to do KCL at node B. This is our next unknown node. We got I2 and I3 going in, I5 coming out. I2 plus I3 minus I5 is 0. So I2, we've actually written it before, so it's VA minus VB divided by R2. I3 is V2 minus VB divided by R3. And we're adding I3, and we subtract off I5, which is VB minus VC divided by R5. And this will be equal to 0. So here's our second equation. And for our last equation, we're going to do KCL at node C. So looking at node C, we've got I5 and I4 going in, I6 coming out. So I4 plus I5 minus I6 is 0. And we've written R4 or I4 before, it's VA minus VC divided by R4. We've written I5 is VB minus VC divided by R5. And then I6 is VC minus 0 divided by R6. So VC minus 0 divided by R6. And this gives us our last equation, for this system that will allow us to solve for VA, VB, and VC. So moving on to part C, it says what can be said about the voltage across R2 with respect to the voltage across R4. So if we take a look at this diagram, so VR4, all right, so just taking a look at this, it's from A to C, and VR2 is from A to B. So actually VR4 is equal to VR2 plus VR5. VR5. So clearly VR2 is less than R4. So VR2 is less than VR4. Just since we need to add another term in order to get to R4. So then last part, we're drawing in a voltmeter to measure the top right node voltage. And so I'm just going to draw a little label there. So the idea of measuring a node voltage is we take the positive end of our voltmeter to that node, and we take the negative end back to ground, right? So node voltages are with respect to ground. If I were to ask you to measure the voltage across a particular component or device, right, you would measure between that device. So if I wanted to measure the voltage across R2 here, it would be there and there, right? So hopefully that makes sense. You might ask for that instead, but we'll see. So that's for the first question. Hopefully that feels pretty familiar. Moving on right along here. So we're going to derive an equation that describes this unknown node voltage V out. So what is our unknown node voltage? Well, we know that this bottom node is ground, so that's 0. And we know that V in is kind of like a voltage source, so that's always going to be whatever V in is. And then this is our unknown voltage, V out. So to derive this equation, I'm just going to define some currents again. So here's IR going into that node, IC coming out. So IR minus IC is equal to 0. That's by KCL again. So then what is IR? Well, IR is V in minus V out divided by R. And what is IC? So if you forget the device physics, the current through a capacitor is given by the capacitance times the derivative of the voltage across that capacitor over time. So we do C dV, and the voltage across the capacitor here is V out minus 0. So it's just V out dt equal to 0. And if we were to rewrite this again, we've got RC dV out by dt minus V out is equal to V in, or sorry, rather plus V out. So I multiply by R and I move the V out terms to the right-hand side. So what does this look like? Well, V out starts at whatever initial value it is, and then it accelerates, right? So we've got some kind of acceleration term towards V in at a rate proportional to RC here. So hopefully that makes sense. And that will kind of help us for this next part if you didn't remember the differential equation solutions. So what happens to V out? So V out approaches V in at a rate proportional to R times C. And if we were to just sketch that, right, so we've got V out, we're looking at V out as a function of time. And if this is V in, right, V in's level, it's that dotted line. And then at T naught, V out's going to stay 0, and then it's going to approach this V in level. So then moving on to part C, what lab equipment would you use to observe this? Well, we've got a voltage source, and it's just a constant voltage source. We can change from 0 to 1 volt. So maybe a DC power supply. And we're looking at something as a function of time, so we'll always need an oscilloscope for that case. All right, so now it says to sketch the setup. So we have our DC power supply, and we have our circuit here. And I'm going to connect the DC power supply. So there's the positive end, here's the negative end here. And then here's our oscilloscope, I'll just call it a scope. And on channel 1, we're going to connect maybe to this input. So there's the plus end of our probe. There's the minus end of our probe, the ground end. And then on this second channel, we're going to observe the voltage across this capacitor here. Then part D asks, how would you ensure that this data is collected around time that V in transitions? And to do so, we would use a trigger. On channel 1, since in my setup drawing, I've connected channel 1 to that input. On channel 1, set to maybe about half a volt and rising edge. And so I want you to fully specify how you are going to ensure that this happens. So we're going to set a trigger. Once that trigger is triggered, it's going to start collecting data. So that is number 2 here. For number 3, we are looking at this circuit, and it now has an AC input here. So we're going to be using the impedance model. So I'll just write J omega L here. And we are deriving an equation that describes an unknown node voltage V out. So this is known. Again, this is V in. This is our unknown node. So this is V out. Right? So what is V out? V out is, well, there's some current here in this loop. Right? So it's actually this current times R. And what is that current? So the current is this input voltage, right? And I'm using this different approach than the other one, but you should just know that you can use any kind of method to solve this. So in this example, I'm just going to use that current times R. So that current is I, or V in, divided by the magnitude of this equivalent voltage, right? So this Z EQ here, we'll just call it. since Vn is specified in RMS, that current is also going to be in RMS, which means that we need to take the magnitude of our impedance. Whenever something's in RMS, it's an average, or it's not necessarily including the imaginary components anymore. So we've got our current here. So that's Vn divided by the square root of R squared plus the imaginary component, which is omega L squared, which means that our output, V out, is, Vn divided by this, R squared plus omega L quantity squared times R. And, that gives us an expression here for the output voltage. So for part B, we're describing what happens to V out considering omega. So V out, right, we've got omega in the denominator there. So as omega increases, V out decreases, right? So V out is inversely proportional to omega. And we can actually see that when omega is 0, so here's omega. When omega is 0, we've got, the square root of R squared in the denominator, which is just R, and we're multiplying by R. So that just means that at omega 0, V out is Vn. So if we're plotting V out, well, at omega equals 0, we're at this level of Vn, and we're decreasing as omega increases. So that is a sketch of that behavior. So looking at part C, what lab equipment would we use? So we're going to be looking at something that's changing over time again. And we're also using an alternating current source. So that should be a clue that you'll need a function generator. And you'll need an oscilloscope. Right? Or a digital multimeter, right? We could also measure the voltage level. But I'm just going to draw it within the oscilloscope because I see the next question asks about 2 periods of data, which is something that you can only do with an oscilloscope anyway. So let's draw our function generator. And then our circuit. I think the inductor came first here. Yeah. So on the function generator, we've got channel 1, and we're taking the positive end to this inductor, the negative end to the resistor. And on the oscilloscope, we've got channel 1, and we're taking this to the input side, right? So across the entire network. And on channel 2, we're just looking at this voltage across the resistor there. All right, so for part D, right, again, it says, what equipment settings would you change to capture 2 periods of data? And if you'll remember, so on the oscilloscope, when we're looking at the time, when we're looking at changing the time, this is the same as changing that horizontal scale. So change the horizontal scale. And we would zoom in or out to that signal there. So hopefully that question makes sense. For this next one, we are looking at kind of like a second order filter here, super fun analysis. So we're going to start off by deriving the Thevenin equivalent circuit seen by the branch containing R2. So this whole section is a branch, right? So that's a branch. This is a separate branch, but we're just considering this section, this branch containing R2 here. So I'll redraw my circuit. That's C1, R1, and this is now removed so that we can find the open circuit voltage. And so VOC, which going back down to this reference, if you forget, the Thevenin voltage is given by the open circuit voltage, right? So we remove the load, we open it up, and we figure out what voltage is across there. So Vn is specified in RMS. So, I'm just going to use the voltage divider principle here to figure this one out. So Vn is equal to, V open circuit is equal to Vn times R1 divided by, in this case, we have to use the magnitude. So the magnitude of 1 by j omega C1 plus R1, which in this case, that magnitude, let's rewrite this, R1 divided by minus 1 by omega C1, quantity squared, plus R1 squared, and square root of that. So that's our open circuit voltage. Hopefully that makes sense. You could alternatively, figure out what the current is, and that would be I times R1, but you should be able to arrive at the same result there. So just stick to that. We found the open circuit voltage. And the next thing that we want to do is figure out the short circuit current. Right, and I think a lot of you did this whole process in lecture, so I'm going over how to do it here. R1, C1, Vn. So what happens when we have a short in parallel with the resistor, right? So that equivalent resistance is 0 times R1 divided by 0 plus R1. So that equivalent resistance ends up going away. Whenever you have a short in parallel with a resistor, the resistor effectively goes away, right? So all the current is going to take that short path. So our I short circuit is then given by Vn divided by the magnitude of this j omega C1, 1 divided by j omega C1, which is the same as Vn divided by 1 by omega C1 minus 1 by omega C1 squared, square root, which is the same as Vn divided by 1 by omega C1, which is simply omega C1 times Vn. So there's our I short circuit, and then to figure out our Thevenin impedance, right? So this is the magnitude, since we have everything in RMS. Our Thevenin impedance is given by V open circuit divided by I short circuit, which is Vn times R1 divided by this mess. So minus 1 by omega C1 squared plus R1 squared square root. So that is our open circuit. And then the I short circuit is omega C1 times Vn. So these Vn ends up canceling. I'm going to erase them here. And that is our magnitude of our impedance there. And that gives us, part A. So for part B, we are now looking at what happens to the Thevenin voltage considering omega. So just taking a look at our Thevenin voltage, right, as when omega is 0, we've just got a term in the denominator that blows up to infinity. So our Thevenin voltage is 0. And as omega increases, then our Thevenin voltage goes up. So Thevenin voltage increases proportionally to omega. And we said at omega equals 0, the Thevenin voltage is at 0. And so it increases over frequency. So that is the plot. The next part is, so we're going to suppose that V out is across C2, and we're going to determine some transfer function. So let's draw out our circuit here. We got C1, R1, R2, C2. And we are calling, so this was already defined as ground, and we're calling this our output voltage, and this is our input voltage. So our goal is to figure out that transfer function. So how do we do this? Well, it looks a little complicated, but fortunately, we figured out the Thevenin equivalent circuit for this. So we can actually just do this. We can replace that with this. So our Thevenin impedance there, and we have our Thevenin voltage here. And this is now R2 and C2 in parallel with this equivalent circuit that we just found. So we've got R2, C2, and V out is now whatever this current, now I'll do this current thing instead of using the voltage divider principle, but you could also use the voltage divider principle. So V out is I times C2. So what is I? Well, we're applying V Thevenin over this whole network. So ZTH is already given as a magnitude, right? So we've got this, right? So there's that. And then we want to figure out the magnitude of the rest of this. So R2 plus 1 by j omega C2. If you're looking for the magnitude of this. And we're multiplying, right? Okay, so that's that current there. So rewriting this, V out is V Thevenin. I'm just rewriting that I term. So ZTH plus R2 squared plus 1 by omega C2 quantity, right? So this is actually negative, this squared, and the square root of all that, times C2, or times the magnitude of C2, rather, since we're looking at RMS things. So this is times negative 1 by omega C2 quantity squared, or squared and the square root. So these guys cancel out, rather. All right. And that's no longer negative since we're squaring it and then taking the square root. Okay. So there is our V out. And V Thevenin is already in terms of V in. So if we were to expand this out one more time, V out is equal to V in. So I'm writing out V Thevenin here times R1 divided by 1 by omega C 1 squared plus R1 squared square root. That's our V Thevenin. And then we divide by this whole thing. Copy that over and multiply by 1 by omega C2, which then gives us, right, if we divide V in over, that is our transfer function, unfortunately. And I've got this in omega. I think I'll ask for it in omega instead of s, just so that this is no longer difficult. So then for part D, we're asking what happens to V out when omega is 0. And just looking back here, right, so when omega is 0, our Thevenin voltage should become 0. And that's because we have this capacitor in that first stage. So this capacitor in the first stage, ends up blocking all the current through the system, which then causes our V out, which is here, to be 0. So so V out equals 0 when omega equals 0. All right, so this was a bit of a challenge. I think I'll probably have something that's easier, a little bit easier than this question on the exam, but good practice. And so for this final question, it's more of like a design kind of question since that was part of the course a little bit. So it says, suppose we're designing a tuner and that outputs a voltage proportional to the proximity of an input voltage to some target frequency. And, since that output voltage, that level of the output voltage is proportional to that proximity, that should give you a clue for this first question that the magnitude is a more important metric, right? So when we're closer to that input frequency or that target frequency, our output should be greater. So magnitude, right? And then we want, when should maximum transfer occur? So maximum transfer should occur when we're at that target frequency. When omega equals omega naught, I suppose. Right? So when that input frequency omega is the target frequency omega naught, and then if we were to sketch this desired transfer, then at omega naught, this is going to be whatever the maximum transfer is. So we'll just draw this here, and then it should taper off, about omega naught. And that's kind of like the response that we want. So on this vertical axis, we've got the transfer, right? So the magnitude of V out divided by V in on that vertical axis there. So the next part says what lab equipment would we use? Also, we're inputting some kind of sinusoid or anything with a frequency really. And to do so, we would use a function generator. Since a DC power supply can't really give us any kind of frequency. And it says to sketch the setup. So we'd also probably want maybe a multimeter, like a DMM, digital multimeter, just to measure that output value. So then we would have a function generator, we would have our tuner, and then so that tuner has an input terminal and a ground terminal, and then it has some output terminal. So on the function generator, maybe on channel 1, we would go in here, the plus and minus, right? So the positive and ground. And then we would measure the output voltage with our multimeter. So measuring voltage, and we measure the voltage across V out and this reference ground of the tuner circuit. So describe an experiment to validate the device performance. So we would measure the output voltage, maybe keeping the input voltage constant, but varying the frequency to, kind of like plot something similar to what we wrote out in B, right? So we wrote this plot out and we would change the frequency. So as we get closer to omega naught, the transfer, right? So that ratio of the output to the input should increase and be maximized at that target frequency. So I think that, yep, that's the end of this practice exam. And like I said, number 4 here, a little bit more difficult than what I'd be expecting of you, but everything else I'd say is pretty fair game. So thanks for tuning in. I'll see you guys next time.